Most RAG systems work by chopping documents into chunks and stuffing them into a vector database. PageIndex does the exact opposite. PageIndex is a reasoning-based RAG framework that completely removes vector databases and arbitrary chunking. Instead, it reconstructs a document's semantic structure, a hierarchical table of contents, so agents can navigate information the way a human researcher would. Hey, everyone, I'm the digital avatar of Rohan Sharma. While the real Rohan is busy solving enterprise problems with AI agents, I'm here to help you understand complex code bases faster than reading documentation ever could. Think of PageIndex like a smart archivist. Instead of shredding documents into confetti and storing them in random boxes, it reads the entire content, rebuilds the original table of contents, and files every page exactly where it belongs. In this video, we'll reverse engineer how PageIndex does this, directly from the code, and you'll see why this approach challenges the standard RAG architecture. We begin in Run PageIndex PI, the entry point. Using argparse, we define the inputs. Aside from just the PDF path, notice arguments like TOC pages and max tokens per node. These are the tuning knobs for our archivist, determining how many pages we scan to find an existing table of contents and how large we allow a single section to grow before we force a split. Here is a critical guardrail. We enforce an explicit choice. You provide either a PDF path or a MD path, but never both. This XOR condition prevents ambiguity right at the start, ensuring the system knows exactly which processing pipeline to spin up. We take all those CLI arguments and wrap them into a config object called opt. This object acts as the context for our entire run. We then pass this opt directly into PageIndex main. This function call is the bridge from our orchestration layer into the core reasoning engine. We've landed in PageIndex main. Before we can do any reasoning, we need raw material. We call getPageTokens to parse the PDF document. This converts the binary PDF into a page list containing the text and token count for every single page. This page list is the raw data our LLM will reason over. A quick detour to utils p1. GetPage.tokens is interesting because it supports two different engines, PIPDF2 and PyMUPDF. We iterate through every page, extract the text, and calculate its token length immediately using TOC-style. This pre-calculation is crucial because we need to fit these pages into LLM context windows later. Inside Tree Parser, we face a decision. We call checkTOC to see if the document already has a table of contents. If it does, we use process-TOC with page numbers to parse it. If not, and this is the common case for messy documents, we fall back to process-no-TOC to generate the structure from scratch using reasoning. In process-no-TOC, we get creative. We group pages into chunks using pagelist to group.text to maximize our context window usage. Then we feed the first chunk to generate TOC in it. This prompts the LLM to effectively hallucinate a structured table of contents based purely on the text content it sees. This is the aha moment of the entire framework. We don't trust the LLM blindly. Inside Metaprocessor, we immediately run verify TOC. This checks if the generated page numbers actually match the content. If the accuracy is decent, say over 60%, but imperfect, we enter a self-correction loop with fix incorrect TOC with retries. This is the reasoning part of the RAG. It's surprisingly grounded. We take a node and its supposed physical index, page number. We grab the actual text from that page in PageList, and we ask the LLM a simple question. Does this section title actually appear here? This ground truth check prevents hallucinations from breaking our retrieval index. This is the clever part. We look at the neighbors. We find the prev-correct node and the next-correct node. We know the missing section must be somewhere between them. We combine the text of those intervening pages and ask the LLM to pinpoint the section within that narrowed range. Its binary search meets semantic reasoning. We handle scale recursively. If a generated node covers more pages than max page num to each node, we call meta-processor again just on that node's content. This fractal approach ensures we have granular resolution even for massive chapters, drilling down until the tree is perfectly sized. In PageIndex d.py, parsing headers seems simple until you remember code blocks. A hash symbol inside a code block isn't a header, it's a comment. We handle this with an in-code block state toggle. As we iterate lines, we flip this switch on triple backticks to ensure we never mistake code for structure. We call this tree thinning. If a node and all its children combined have fewer tokens than min-node token, they are too granular to be useful indices. We identify these lightweight branches and merge their text up into the parent. This pruning process creates a denser, more meaningful tree for the LLM to reason over later. Back in utils.py, we have our API wrapper. Notice the finish reason return value. If the model gets cut off because the table of contents is too long, we need to know that so we can prompt it to continue, rather than treating it as a completed response. It's a small detail that makes the system robust for real-world documents. By avoiding vector databases and chunking, PageIndex builds a retrieval system that mimics how humans navigate documents, via structure. We saw how it extracts a tree, verifies page numbers by looking at the content, and self-corrects when it gets lost. This architecture provides higher interpretability and often better accuracy for long context reasoning tasks. Happy coding, everyone! If this walkthrough helped you understand the system better, do like, share, and subscribe. It really helps the channel grow.